Hello, everyone. I hope you are doing well. And this is the last video lecture on this PID controller. That is part 3 of this PID controller video lecture series. So in this video, we will solve some typical questions or basic simple questions on PID controller. So I hope before you watching this video, you have completed already the part 1 and part 2 video, which based on the theory of this PID controller. After that, you can solve these problems. Okay. Now, without further ado, let me share my screen and solve the questions, 2 or 3 questions on this PID controller. I hope you can see my screen right now. Okay. Let me share my PPT and directly solve these questions. So as usual, I will start with the quote of the day. And today's quote of the day from a great personality and national hero of our neighboring country, Nepal, Mr. Tenzing Norgay. He first invaded the Mount Everest to travel, to experience and learn, that is to live. So what a life. Their life and their stories always motivates us. So with this motivation, we will start our lecture today. Yeah. So let's consider a system. GS is equal to 1 by S minus 2 with a unity feedback subjected to a unit step input. So find out the closed loop transfer function. The first question is super easy. As you all know that GS is given and unity feedback is also it is mentioned. So that means you can take HS equal to 1. So once GS and HS is given, so you can calculate the transfer function as GS by 1 plus GSHS, since it is a negative feedback. So that's why it is plus. Okay, 1 plus GSHS. So if you put the value of GS and solve, then you will get this kind of answer. Probably 1 minus, this is just a simplification, nothing much. So S minus 2 will cancel out and it will be 1 minus 1. Yeah. Okay. So this is the answer for the first question. Okay. So let me draw it, or rather erase the whole screen and write down the answer right here, S minus 1. So this is the closed loop transfer function. Okay. Fine. Now draw the closed loop system response. So for that, question number B, let's say CS by RS is equal to 1 by S minus 1, of course. Okay, that means output by input transfer function. So what we can say, CS is equal to 1 by S minus 1 into RS. Now this R input RS is equal to 1 by S. Why? Because as you can see here, it is subjected to a unit step. So unit step function, RT equal to 1 and RS equal to 1 by S. So we can write here 1 by S. So basically this is multiplied here into RS. So RS is equal to 1 by S. So we can write this, right? So from here you can easily see that how to get CT by taking inverse Laplace transformation. For that I need partial fraction method. So let be A plus S by B plus S minus 1. If you calculate the partial fraction method, due to time shortage, I am not solving the each step. But here the A value will be minus 1. You can easily determine by partial fraction method A equal to minus 1 and B equal to plus 1. Okay. So this will be the CS. Now after taking inverse Laplace transformation, CT, small ct equal to minus 1 plus e to the power t. So this is the answer for the draw the closed loop system response. Now the question is how it looks like. It is perfectly fine answer, but if you want to visualize it, so how it looks like. So for that, suppose how this -1 looks like. The -1 signal looks like this one. That is the -1 value, right? Okay. Let's say this is 0. So -1 looks like this one. Okay. Understand? So this is -1 signal. What about this e to the power t? E to the power t, it looks like this one. Why we are starting from this particularly 1? Because as you know, e to the power t at t equal to 0, what is the value of e to the power t? It will be 1. Okay, so that's why the starting point equal to 1. And at infinity, e to the power infinity value evaluates to infinity. So that's why it is like this. Okay. Now, if you add this equation number 1, I mean figure 1 and figure 2, if you add, then what we will get? You will get a curve like this one. Okay, not exactly matching, like this one. Why I am claiming that this is my output? Why? Because as you can see that -1 plus 1, it will be 0, right? So that will be the effective answer. Okay. Similarly, infinity plus of -1 plus infinity, what will be the answer? Infinity. So that's why ultimately this is the thing. I hope you are getting my point. So since the output is, it looks like this one, so of course this is the actually closed loop system response. Comment on its stability. By seeing this figure, you can easily comment that it is totally unstable system. Why? Because there is no bounded output. There is unbounded output. So that means it is unstable system. Again, someone can also comment the stability from this one itself. As you can observe, this system has only one pole at right hand side at +1, right? Since the one pole is at right hand side, this is a bad pole, so it causes instability of the system. Okay, so that's why this is not stable. Now the question 4th is important for this lecture. For this lecture video, that is PID controller. So can you design? So this system is, please remember, this system is ultimately a unstable system, right? Now the question is, can we design a suitable PID controller to make this system stable? The answer will be probably we need to check basically. Okay, so for example, how to, please concentrate over here. Suppose this is your RS, this is your comparator, then this is your system 1 minus, what was there, S minus 2, right? S minus 2 is there, and output CS, and this feedback is given as 1. Okay, fine. Now if I introduce a controller, so I need to introduce controller in between error and comparator and the plant, right? So what kind of controller I will introduce? PID controller. So that means here it will be, you need to write KP plus KDS plus KI by S. So those who cannot understand, this, why I am writing KP plus KDS plus KIS, you please refer to my earlier videos, it will be clear. So KP plus KDS plus KIS, right? So if I apply this PID controller over here, then can you tell me what is my new GDS test? Because GS is something different, 1 by S minus 2, that was our GS, but now it is modified. Now G dash is, you can write like this one, like this one, KP plus KDS plus KI by S into 1 by S minus 2, right? Am I correct? So this is G dash test. What is my HS? HS is still same, that is 1, right? So now what is the closed loop control system? If you calculate from here, so the closed loop control system may be G dashed by 1 plus G dashed H, correct? Okay, so if you calculate this transfer function, since I have already calculated this transfer function, you please calculate from your own copy and simplify this G dashed and 1, then you will get the transfer function will be in this form. Let me write it. KD KD SS square plus KPS plus KI. So I request all of you, please verify these results, okay? For better understanding, I am just writing the answer here directly. SS square plus KP minus 2S plus KI. Okay, so let's say this is the transfer function I am getting of this closed loop control system. This is my transfer function. Now, as you can see, what is the characteristic equation here? The characteristic equation here, we can write it from the denominator, right? So KDSS square plus KP minus 2S plus KI equal to 0. Now the thing is very simple. Uh, uh, can you give me an example of stable system? Okay, one second. Um, just a minute. Yeah. Uh, my question is, can you give me a characteristic equation which is stable? Answer is of course, like this one you can take. S square plus 3s plus 2 equal to 0. Why this is a stable system? Because you know there are two roots, both are at negative side, minus 1, minus 2. So if somehow we can convert this system into this one, not only, I mean, I am taking any arbitrary question. You can also take minus 1, minus 3 also. That is also possible. No problem. Okay. I am taking minus 1, minus 2. You can take minus 10, minus 20, minus 1, minus 4, any kind of thing. At least both should be in negative half. Okay. So for that, this is our characteristic equation. So if I somehow convert this bad equations into a good equation, then only we are done. So from that, can we calculate, comment anything? Yes, by comparing the coefficient, 1 plus KD should be equal to 1. So what is the value of KD? KD value equal to 0. If you place KD equal to 0, then done. Then KP, what is KP minus 2 should be equal to 3. So what will be the value of KP? Come on, it is 5. Okay, and similarly, what is the value of Ki? 2. So done. Okay, so Ki 2, Kp 5, Kd 0. So that means we need to introduce a PI controller basically to, control this system. So if you employ this Kp, Ki, Kd value over here, then you will see the ultimate output graph will looks like somewhat kind of this one. I'm not, I mean, you can verify through it MATLAB, okay, but I'm not drawing it, here, but you can verify MATLAB. If you place Kp value 5 here, that means 5 plus Ki value 2 here, that means 5, uh, 5 plus 2 by S. If you just use this one and multiply this one and take the transfer function, or rather you can, directly apply Kp value 5 here and Ki value 2 here. So if you take this transfer function, then you will see this will be the output. So initially the output was like this, unbounded, but this is the modified output, which is very, stable output. So PID controller, or rather PI controller, gives me the power to stabilize a system. Okay. So I hope this part is clear to you. If it is not clear, then go back to the initial portion and again try to, analyze this question. Okay, fine. Now, coming back to the next question, it is again kind of similar question. Here, one question is, GS and HS is given. What is the damping factor of the above system? Okay, so what is the damping factor? So for that, we need to calculate the closed loop transfer function. So closed loop transfer function will be 16 by SS square plus 16, 1.6S divided by 1 plus 16 by SS square plus 1.6S into 1. Okay, so ultimately 16 by, it will become 16 by s square plus 1.6s plus 16. So this will be the closed loop transfer function. So from here, we can easily determine the omega n equal to 4 rad per second, correct? And 1.6 is equal to 2 zeta omega n. Okay, so this one. So from here, you can find out zeta value equal to 0.2. Very easy question for the question number A. Okay, fine, done. I think it is clear. Now, for this omega n, when you get this omega n zeta, you can easily calculate the maximum overshoot. I mean, however, it is not required for this question, just an observation. MP you can calculate, right? That means the formula is e to the power minus psi pi by 1 minus zeta square. So if you get this zeta value, then you can easily calculate MP value. And it is turning out to be, in case of 0.2, the MP value is 52%, almost 52% overshoot, which is very bad, I guess. Okay, which is very bad, this 52%, I mean, uh, overshoot. So can we do something to how to minimize this overshoot? Answer is D controller we need to introduce, right? PD controller. So that's why the question PD controller, and which essentially increase the damping ratio from 0.2 to 0.8 basically. Okay, so fine. The question is design a PD controller so that the damping ratio becomes 0.8. That means oscillations will less. Okay. Now, how to increase the damping ratio? That's here we need to use a PD controller, right? So this PD controller, what is inside this PD controller? It is Kp plus Kds. Okay. So what will be the again now convert? I mean new G dash. What will be new G dash test? It looks like Kp Kp plus Kd s into 16 by s square plus 1.6s. I think you all are agree, and hs equal to 1. So using this fact, I mean using this, you can easily create the transfer function of this one, or t dash s modified transfer function. This will be g dashed by 1 plus g dashed h, right? So if you calculate, I am writing it directly, the answer will be 16 kds plus 16 kp, it comes from this end, divided by s square plus 1.6 plus kd into 16 s plus 16 kp. Okay. Now the question is, look, designing a PD controller means you need to find out kp and kd value basically. Okay. Kp and kd value you need to find out. So can you tell me what will be the kp value? The kp value should be 1. Okay. Why? Because if it is not 1, then this will change the, I mean, natural frequency of the omega n of the system, right? Which is not possible. So that's why omega n, to become omega n equal to 4, so that means kp should be 1. So let's say kp equal to 1. Now, 2 into zeta into omega n, that is 4, is should be equal to 1.6 plus kd into 16, right? Now, what is desired zeta? Desired zeta is 0.8. That means we need 0.8. Okay, we need 0.8. So for 0.8, can you calculate the KD? Answer is of course yes. If you solve this equation, you will get KD value equal to, just verify, okay, later on, KD value will be 0.3. So once you know this answer, so that means here PD controller, the controller is 1 plus 0.3s is our PD controller, which is situated here along with the GS. Okay, so and if I use this PD controller, then my zeta becomes 0.8 And if you calculate with the help of zeta, what is the maximum overshoot? The maximum overshoot will be turning out to be 1.5%. So see how drastically PD controller helps us to reduce this maximum overshoot. It is coming down from 52% to 1.5%. It is a huge improvement. So by using this KD, you can, KD and KP value, you can reduce the um, overshoot. Okay. So in this way, you can design any kind of controller. I hope this concept is clear enough. So basically, when the two things you need to remember, when in case of PID controller, you need to place the PID controller here. And after PID controller, G will become G dashed. This is the combination G dashed. And then you need to find out 1 plus G dashed for closed loop control system, provided unity feedback. Otherwise, you need to find out G dashed by 1 plus G dashed I. And then you need to calculate, by comparing the characteristic equation, you need to find out zeta or something else. Or through that, by comparing, you need to find out Kp, Ki, Kd value. That's the objective of the problems. Okay, so I think these two problems will give you a fair enough idea on PID controller. For more problems, please go through any standard book, and in probably in class we will solve more higher standard questions. Okay, so thank you.